The James Webb Space Telescope has just dropped a bombshell in the world of physics, shattering what scientists thought they knew about the universe with a single stunning image. It's rewriting the rules and ending a fiery debate that's raged among scientists. Webb's latest capture is not only visually fascinating, but it's also an eye-opener that's enhancing our understanding of the cosmos. Get ready to rethink everything. The crisis in cosmology refers to a significant and persistent problem in astrophysics. The age and expansion rate of the universe as estimated by different methods do not agree. This discrepancy has puzzled scientists and sparked a series of debates and research efforts to understand the underlying cause. Cosmology, the study of the universe's origin, structure, evolution, and eventual fate, has made substantial progress over the past century. The Big Bang theory, which suggests that the universe has been expanding from a hot, dense initial state for about 13.8 billion years, is the prevailing cosmological model. This expansion is characterized by the Hubble constant, a value that represents the rate at which the universe is expanding. There are several ways to measure the Hubble constant, and broadly they fall into two categories: local measurements and early universe measurements. Local measurements involve looking at astronomical objects within the universe, such as Cepheid variable stars and Type Ia supernovae. These are known as standard candles because their intrinsic brightness is well understood, allowing astronomers to calculate their distances from us. By measuring the speed at which these objects are moving away from us, thanks to the expansion of the universe, scientists can estimate the Hubble constant. On the other hand, early universe measurements are derived from observations of the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. The CMB is a snapshot of the universe at a much younger age, only 380,000 years after the Big Bang. By studying the slight fluctuations in temperature and polarization of the CMB, scientists can infer not only the age of the universe but also its rate of expansion. The crisis emerged when astronomers realized that these two methods were giving significantly different values for the Hubble constant. Local measurements suggest the universe is expanding faster than what is predicted by observations of the CMB. This discrepancy suggests that there may be new physics at play that we do not yet understand, or there could be systematic errors in one or both sets of measurements. The advent of the James Webb Space Telescope brought fresh insights into this problem. With its unprecedented resolution and sensitivity, the JWST has been able to look further back in time and at fainter objects than ever before. It was anticipated that the data from JWST would help refine the measurements of the Hubble constant. However, early observations have seemed to complicate the picture even more, providing new data that may not fit neatly within our existing models. The implications of this crisis are far-reaching. If the discrepancy is due to new physics, it could require revision of the standard model of cosmology. For instance, there could be previously unknown particles or forces affecting the universe's expansion. Alternatively, it might hint at the need for a new understanding of dark energy, the mysterious force that is thought to be accelerating the expansion of the universe over time. Theories in cosmology have evolved as new observations have challenged existing models. For instance, the discovery of the CMB in 1965 provided strong evidence for the Big Bang theory and against the steady-state theory, which posited that the universe has no beginning or end in time and is always expanding at a constant rate. Similarly, the discovery of the accelerating expansion of the universe in the late 1990s led to the introduction of dark energy, a concept that was not part of the original Big Bang theory. Each time new data has been introduced, cosmologists have had to examine the robustness of their theories and, in many cases, develop new theories or modify existing ones to account for the observations. The current crisis may similarly lead to significant advancements in our understanding of the universe. While the crisis in cosmology presents a formidable challenge, it is also an exciting opportunity. It drives technological advancement, as scientists require more precise instruments to make better observations. It fosters collaboration across international and interdisciplinary boundaries, as understanding the universe is a question that intrigues nations and fields alike. Most importantly, it exemplifies the dynamic nature of science, where knowledge is never absolute but constantly evolving as we expand our horizons and deepen our understanding of the cosmos. Cosmology, the study of the universe's origin and evolution, has faced a new challenge beyond the well-known Hubble tension, the S8 tension. This tension centers on the distribution and density of matter in the universe, a fundamental aspect that helps us understand the cosmic structure and its history. The concept of lumpiness refers to how matter is not evenly spread out across the cosmos. Some areas are dense with galaxies, while others are vast voids of almost nothingness. Scientists use different methods to measure this lumpiness, and that's where things get tricky. One method is through low redshift observations, particularly with weak gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster, warps the space around it and bends the path of light passing by. This effect allows astronomers to map the distribution of dark matter, the unseen stuff that doesn't emit light but has a gravitational pull. Weak gravitational lensing involves looking at the subtle distortions in the images of distant galaxies caused by the less dense and therefore weaker gravitational fields of large-scale cosmic structures. On the flip side, scientists examine the cosmic microwave background, CMB, which is the afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying with it information from the early universe. By studying the CMB, scientists can infer the early lumpiness of the universe, which should align with the large-scale structure we see today. Here's where the S8 tension comes in. These two methods don't agree. The clumpiness measured from the CMB suggests a smoother distribution of matter compared to what is observed directly in the nearby universe using gravitational lensing. This discrepancy points to a possible gap in our understanding of the universe's evolution from its smooth beginnings to its current clumpy state. The resolution to this tension could lead to revolutionary changes in cosmology. If the measurements are accurate, it may hint at new physics, requiring an update to the standard model of cosmology, the framework that describes the dynamics and content of the universe over time. Theories of the universe have evolved dramatically. For instance, the Big Bang theory, which posits that the universe began as a hot, dense point and has been expanding ever since, was once contentious. Evidence like the CMB and the observation of the expanding universe has since turned it into the leading theory of cosmic origin. Another area where our understanding has progressed is dark energy. In the late 1990s, observations of distant supernovae revealed that the universe's expansion is accelerating, not slowing down as previously thought. This led to the concept of dark energy, a mysterious force driving this acceleration. Its nature remains one of the biggest questions in cosmology. The James Webb Space Telescope, JWST, is poised to push the boundaries of our cosmic knowledge further. With its unprecedented resolution and sensitivity, JWST will peer into the earliest epochs of the universe, examining the first galaxies and stars. It will also refine our measurements of cosmic expansion and the distribution of matter. Addressing the S8 tension will require meticulous observation and possibly new theoretical insights. Whether the resolution lies in understanding dark energy better, accounting for the behavior of dark matter, or finding entirely new physics, the implications will be profound. Cosmology's crises, such as the Hubble and S8 tensions, are not stumbling blocks but stepping stones. They drive the field forward, leading to better instruments, more precise observations, and deeper theoretical insights. Each challenge brings us closer to answering the most fundamental questions about our universe's past, present, and future. When we confront the mysteries of the cosmos, it's like trying to solve the world's biggest jigsaw puzzle without having the picture on the box. Scientists, the dedicated puzzle solvers, are tirelessly piecing together the universe's secrets. They recently upped the game with a project known as Flamingo, which is a nod to the extensive scientific research it stands for. The Flamingo project isn't a usual science experiment. It's a heavyweight of computational might, utilizing one of the planet's most powerful supercomputers at Durham University in the UK. Its scale is so vast that it gobbles up over 50 million hours of computer time and sprawls across 30,000 processors. This is no small feat. It's the scientific equivalent of running a marathon on every continent, back to back. Earlier attempts to simulate the cosmos focused primarily on dark matter, the enigmatic stuff that doesn't emit, absorb, or reflect light, but we know it's there because of the gravitational pull it has on the things we can see. Flamingo, on the other hand, was ambitious. It wasn't just about dark matter anymore. The simulation included everything from the behavior of galaxies to the gas inside them, the stars, and even the supermassive black holes at their centers. It's as if we went from having an incomplete map of the world with only landmasses to one that shows mountains, rivers, and every landmark in exquisite detail. But why go to all this trouble? The goal was clear: to understand the S8 tension better. This tension, a discrepancy in the measurements of the universe's structure, suggests there's something fundamental about the universe that scientists are not getting right. If the measurements were songs, it would be as if one was jazz and the other classical, both music, but distinctly different. Flamingo was supposed to help iron out these discrepancies, to let us know whether we were looking at the universe through the wrong lens. But despite its sophistication and detail, the S8 tension remained. It was like using the most advanced equipment to check your math and still ending up with different answers. What this means is both exhilarating and daunting.